So in this video, we are going to learn about buffers, acid-base buffers, as well as acid-base titrations and different types. Now, buffered solutions we started learning about in the last chapter. And a buffer is a solution that resists changes to pH and contains a weak acid and its conjugate weak base. I'm not going to read all of this. You're going to look through this and you're going to read it. Most of it is on your notes. And we learned in the last chapter we can add a strong acid, H+, to the buffer. The strong acid reacts with the buffer's weak base, just like this, and we form HA, thus getting rid of the H+. Now, if we add a strong base to the buffer, strong base would be OH-, the base reacts with the weak acid in the buffer, forming water and the conjugate weak base, and you notice we end up without any OH-. Hence, the buffer can get rid of H+ through this reaction, or it can get rid of OH- through this reaction. So let's do a problem now. We're going to find the pH when we add some HCl to a buffer system. And you need to fill this in. ICF, that just means we have a limiting reactant. We don't do ice boxes. If we have anything strong, a strong acid or a strong base present, we do what's called an ICE, initial change final. In these ICF, sorry, I said ICE, we do an ICF, very important, ICF, not an ICE yet. ICF, initial change final. Final, not equilibrium, because if you have a strong anything, the reaction goes to completion. We do not have equilibrium. So we set up the reaction and we set up an ice box. We have our H+, the strong acid, and H3, the weak base, forming the conjugate weak acid. We put in our initial row, what we know about the initial concentrations. One quick thing, you can do moles or molarity in an ICF box. Unlike the ice, you have to do only molarity. You're not allowed to do moles in an ice. But we have an ICF. I did molarity here. You could have done moles. Why is this 0.1 molar? Well, we had 0.1 moles of HCl in 1 liter. Molarity is moles divided by liters. So we have 0.1 molar. The change, you got to find out who's limiting. So you look at these two numbers. Now this one's easy because the coefficients are the same for the reactants. They are both 1. Therefore, whichever one of these is smaller is limiting. Hence, this right here is the limiting reactant. These two will go down by 0.1. What happens then, H4 plus? It goes up by 0.1. All right. Now the F final row, remember we just add the I row to the C row to get the F row. So the final, what we end up with is what we started with, initial, minus or plus, however much the change is. And we end up, notice we end up with both a weak base present, 0.15 molar, and a weak acid present at 0.50 molar. Now, our instructions say we're going to use this last row of the ICF box to do an ice box to find the pH. This next step is exactly the same as the previous chapter. We were given a KB, so we will write the KB reaction. And recall, a KB reaction is the base plus water makes hydroxide and the conjugate acid. So you could write that, figure out what it should be, but I'm going to show you right now. Ignore what's on the right side. There's our KB reaction. The weak base plus water makes the conjugate acid and hydroxide. Because bases produce hydroxide, I was given the KB, which is why I wrote a KB, the reaction for a KB. Again, ignore this for now. It's going to come through the ice box here. So now we need an ice box because this is an equilibrium reaction. We have a K, so we have equilibrium. So I put in my initial values will be what was left over from my ICF box. So I put these in here. Oops. Oh, one quick note. I'm going through how to do this, and then later you'll learn you don't actually have to go through this box. in class we'll go over why. But for now, we just take the numbers from the F row, this right here, and we put it right there. I'm going to put that back. The NH4, notice this is NH4, and I put it in the I row for the NH4. And hydroxide starts at 0. There was no hydroxide up here. Now this is just a regular KB problem like we did in class from the last chapter. Minus x, 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 add the two rows, I plus c makes E, and then we plug these into the equilibrium expression. Products, 0.5 plus x times x over reactants, 0.15 minus x. Why do I ignore the water? Hopefully you said in your head, because it's a liquid. Okay, so we get that equation, and then I get to ignore these x's because I don't want to have a crazy quadratic. And the reason I can assume that x is much less than these numbers is because I have a tiny k. The only time we get to assume x is tiny is if our k, our equilibrium constant, is much less than 1. Well, 10 to the negative fifth is tiny. So I get to make this assumption. You should always write down what your assumption is. And now I will solve this equation right here for x. And I get x is 5.4 times 10 to the negative 6. Now notice x is hydroxide, and the question asks to find the pH. So knowing x, which is the hydroxide concentration, I can solve for POH right here. And then because POH plus pH is 14, I can solve for the pH. All right, now here's the note. In class, you're going to learn you have to do the ICF box. When you have a strong anything with a weak, so strong acid, weak base, or if you had a strong base with a weak acid, you always do an ICF because strong acids and bases react completely to the right. Now this piece you're not going to have to use, and you will learn in class what you do instead. And I will tell you right now, you just take the numbers from the F row, plug them into the KB expression. So notice right here, my KB expression would be products. Oops, I'm sorry. That didn't look right. The KB expression is NH4 plus times OH minus, which is 0.5 plus x, so I have the 0.5 here. And x is the unknown, that's my hydroxide. And I divide by my reactants. There's my reactants right here. Notice that's the same as the NH3 right here. So you again, I will go over this in class. But the KB expression is NH4 times OH minus over NH3. We know the NH4, we know the NH3, the OH minus is the unknown, so that's our x. We solve for that, solve for POH from knowing the OH minus, and get the pH. Okay. All right, buffering capacity and some other buffer problems. So buffering capacity, that's how much hydroxide or H plus a buffer can get rid of. So the more moles you have of your weak acid and base, the more OH minus and H plus you can remove that has been added to the buffer. So the larger the moles of weak acid and base, the larger the buffering capacity of the buffer. It's a little repetitive now, isn't it? Okay, quick problem. Which buffer has a bigger capacity? One that is 1 molar in its weak base and conjugate weak acid, or one that is 0.5 molar in its weak base and conjugate weak acid? We just learned we need more moles. So this is assuming they have the same volume. I should have specified both 1 liter or both the same volume. So the one with the higher molarity will have more moles, so that one will have the bigger buffering capacity, 1 molar. Okay, now how do you pick a buffer to use? This is not a difficult problem to do. What you look for is, if you want a buffer at a certain pH, you want the pH to stay at a certain number, this time we're going to pick 4.3, you find a conjugate acid base pair where the pKa is equal to the pH. What does that mean? The pKa, this little p literally means negative log of whatever is after the p. So pKa is negative log of Ka. So you want to find an acid whose pKa is closest to the pH you're looking for. So what we would do is just calculate all the pKa's of all of these acids. Whichever pKa is closest to 4.3, we pick that acid, we would use that acid and its conjugate base. You can go ahead and do those calculations. I'm about to show you what the calculations are, but you should probably check to make sure you're doing this properly. You're just doing negative log of each of these numbers. This is what you should get. We want one closest to 4.3, so we pick C, benzoic acid. There we go. Okay, moving on. Titrations and pH curves. Okay, so that's now filled in. A titration curve is a plot of pH versus volume. pH is on the y-axis, volume is on the x-axis. So in your notes, you had an example of a strong or a weak acid titrated with a strong base. So here's the strong acid titrated with a strong base. Here's the weak acid titrated with a strong base. Now, you're going to highlight these bullet points and fill in all this information. For strong acid, notice we started around pH 1. To find where the equivalence point is, you go where there's a sudden shoot up. And so the equivalence point for this particular graph is at 50 milliliters. And we're going to go halfway between where it starts to shoot up and where it stops shooting up. So halfway between here and here would be about right here, which is pH 7 for this red curve. And the pH is always 7 at equivalence for a strong acid, strong base. If you have a weak acid with a strong base, the pH usually starts somewhere between around 3, but as long as you're starting above 2 and below 7, you're starting with a weak acid. So when I say approximately 3, it should be less than 7 and more than 2. Notice the equivalence point. We're starting here, ending here, and halfway between those two, this particular graph, the pH is about 9 at equivalence. Again, the equivalence point is where you have the sudden shoot up. That sudden increase right there. Important for a weak acid, at equivalence, the pH should be greater than 7. And you'll learn later why only the weak base is present. Now, at the half equivalence means you find the volume at equivalence. Here it's 50. Half equivalence would be, sorry, why did I say 50? 25. I said that earlier too. The equivalence point here is 25 mils. 25 mils. Sorry if I confused you earlier. So the equivalence point is at 25 milliliters. Half of that volume is 12 and a half, which is about right here. And at that half equivalence point, the pH is equal to the pKa. So if I wanted to find the pKa for this weak acid, I'd go to 12 and a half mils. I'd go up to the graph for the weak acid, and I would read the pH. And I'm going to do that a little later. So the pKa for this weak acid would be about 5, because half of 25 is 12 and a half. Go up to the curve, read the pH, 5. Okay, and we'll learn this a little later. This piece, you want to copy this down? This is explaining to you why the pKa is equal to the pH at half equivalence, and we will derive that HA is indeed equal to A minus at half equivalence in a moment. Before doing the derivations for why these things are true, I want to also show you the graph for a strong or weak base titrated with a strong acid. These are the kinds of curves you would see. And I've got some summaries down here. And as I said earlier, where you should highlight these characteristics for the other titration curve types, you should highlight these here as well. These are very important. I'm not going to summarize what it says here. You can see it. All right. Let's find out why these things are true. So, first off, equivalence is when your moles of weak acid or strong acid being titrated is equal to the moles of weak or strong base added, which will occur when the curve suddenly spikes up. Okay, the half equivalence is defined as 1/2 the volume of equivalence. So if this is our equivalence volume, 10 mils, half of that is 5 mils right here. This is the half equivalence point. You would go up to your graph and read the pH at that half equivalence point. So on this one, the half equivalence point is a pH of 9. So I would know that the pKa for this weak base, okay, let's go back. The pKa for the conjugate acid of this weak base is 9, which says that the pKb for this weak base is 14 minus 9. Because if pH is 9, pOH is 5, so the pKb for this weak base would be 5. Okay, let's see why this is true. So first let's look at the equivalence point. So here I filled in all the information. So equivalence is defined as the acid and the strong base. Either way, you could have weak, 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 strong, strong, weak, strong, strong. Equivalence means you have equal numbers of moles. If these are equal, then both are used up completely, minus x on these columns, plus x for your conjugate weak base. When we add the I and the C rows, the weak acid and strong base are at 0. The weak base ends up, we have some left. All you have left is the weak base. So for a weak acid, strong base, you will be basic at equivalence because all you have left is a weak base. So that explains on this page why the pH is greater than 7 at equivalence, because you have only a weak base present. So here you saw the words. Now I'm deriving why you have only the weak base left. Now let's look at half equivalence. At half equivalence, you have half as much of the strong base as the weak acid that you started with. That's the definition of half equivalence. When you have half of the original volume, you'll have added half as many moles. So equivalence, the weak base or weak acid is equal to the moles of the strong base or strong acid added right here. When you've added half as much, because it's the volume of the strong base or strong acid added, when you've added half as much of the strong acid or strong base, you're at the half equivalence point, and you have half as many moles of the strong base or strong acid as weak acid or weak base that you started with. So in here, who's limiting? Whichever one's less. This is less. Therefore, the hydroxide is limiting. These will both go down by 1/2 x. Our A minus goes up by 1/2 x. When we get to our F row, we just add the I and the C row to get the F row. And now do you see that these are equal? Woohoo! We just derived that at half equivalence, our HA and A minus are going to be equal. These are equal. Well, I just showed you on the previous notes. Here's our definition of Ka right here. If HA and A minus are equal to each other, which we just derived that at the half equivalence point, half equivalence, our HA and our A minus, do you see they're equal to each other? They're equal to each other, equal to each other. Therefore, from the definition of our Ka, if these are equal, then Ka is equal to H3O plus, right there. And if I do negative log of Ka, which is the pKa, that must equal negative log of H3O plus, which is pH. So that, what we just did was to derive why this second bullet point is true. That when you are at 1/2 of this volume, we'll go to 12.5 mils, because this is 25. At 1/2 of that volume, the pH at this for this graph, the pH at the half equivalence point is your pKa. So the pKa for this weak acid is 5. So we've gone through that. Obviously, I'm hoping you're realizing this is a very important point that I'm making here, because I keep emphasizing at the half equivalence, pH is pKa, pOH is pKb. All right, find the Ka for the weak acid in the titration curve on the previous page. So you're going to draw, I'm going to get a pen here. There we go. All right, so the equivalence point, oh, I cannot draw straight, was right there, 25 mils. So I go to half of that, 12.5 mils. Oh my goodness, I really can't draw straight. And I go to the graph. I only do this for weak acids. Strong acids, we don't talk about the Kas. So I go to the point on the graph, and then I scroll over to the y-axis. The pH here is 5, which tells me my pKa is 5. Well, if the pKa is 5, then the Ka is going to be 10 to the negative 5. Oh, shoot. I don't want you to see this guy. Okay, there we go. Okay, so the pH is the pKa, which was 5, so the Ka is 1 times 10 to the negative 5. All right, let's look at number 2. Find the Kb of the weak base in the titration curve above. So, equivalence, you go to where the graph spikes up, and I can't draw a straight line. It's at 10 mils. I go to half that volume, which is at 5 mils. I draw a line from half of the equivalence volume up to the graph, the titration curve for the weak base, and I draw over to the y-axis, and I find that my pH is 9. That means my pOH is 14 minus 9, which is 5. I really cannot draw with this pen. So if the pH was 9, the pOH is 5, and the pOH is the pKb, and the Kb is 10 to the negative pKb, which is 1 times 10 to the negative 5. All right. Okay, acid-base indicators. We've seen these. They change color. We did titrations in Chapter 4 first semester. Indicators have Kas, and we could calculate all their pKas, which is just negative log of the Ka of an indicator. You want to choose an indicator that changes color at the equivalence point, not the half equivalence point. You want to change color to denote where the equivalence point is. So in these other examples, you want to change color here, not here. So you look at the pH of equivalence for the strong base. Well, with the strong acid, the equivalence point is right here. For the weak base, the equivalence point is about right here. You go halfway between where you start to suddenly shift and where you stop shifting. So halfway between these two is right here, and halfway between here and here is about there. All right. So you pick an indicator whose pKa is close to the pH of equivalence. Oops. So if you have a strong acid, strong base, remember pH 7. So we would pick bromothymol blue. Weak acid, strong base, the pH should be acidic or basic? Basic. So we want something that's basic. 9.3 looks pretty good. You might say phenol red. It really depends on the base that you have, the weak base, and it's how strong or weak that weak base is. But phenolphthalein should be good because we need a basic pH if we're titrating a weak acid with a strong base. This is on the earlier pages, these notes. So which indicator is best for a weak base with a strong acid? In this titration, your pH will be less than 7 at equivalence. So you want something less than 7. You could pick methyl red or bromophenol blue. You could actually pick methyl orange. Any of these three would do. I just wrote methyl red. But really, any of these three would be fine. Okay, now this next page, you don't have to watch this. This next page is very complicated. This is all extra credit type problems. So I'm going to show you the solutions. I'm not going to go through them. You can turn off the video if you want to. You don't have to watch this. I'm going to let you see all of this. If you want to fill it in, you can. It's complicated because you have to do an ICF. You find out all you have left is a weak base. Then you have to do an icebox. This is the only time when you're at equivalence you have to do the actual icebox. Again, totally extra credit. You do not have to know how to do this. All right. Enjoy your evening or day or morning, depending on when you watch this.